Hello. In this series of videos we're going to be taking a detailed look into special relativity. In this first video we'll start by trying to motivate why we need special relativity at all. By the start of the 20th century we already had some pretty good theories of mechanics. We could predict motions of planets and falling of an apple from a tree. So why did we need a new theory? So we're going to start by thinking about relative motion. So let's say we have a man who's standing by the side of a road and he sees a skateboarder going past. And we'll say the skateboarder is travelling at some speed, let's say 3 meters per second. And the skateboarder has a ball and he throws that ball forwards in the same direction as he's moving. And we'll say he throws the ball forwards at 4 meters per second from his point of view. So relative to the skateboarder, the ball is moving at 4 meters per second. Now, if we were to ask the man how fast is the ball moving, he's not going to say 4 meters per second. He's going to see the combination of those two speeds. So if we call the speed of the skateboarder u and the speed of the ball v prime, then the speed of the ball measured by the man is going to be given by v is equal to v prime plus u. So what I've written down here is something called the velocity addition formula. So it allows us to relate two different observers' measurements of the speed of the same object when those two observers are moving relative to each other, in this case with the speed u. Now let's repeat that thought experiment. But instead of a ball, the man is going to be shining some light forwards, again in the direction of his motion. Light in a vacuum and pretty much in air travels at a speed that we call c, which is 3 times 10 to the 8 meters per second, so 300 million meters per second. And again we're going to call that speed v prime, so that's the speed with which the light travels as measured by the man on the skateboard. We'll say the skateboard is going a little bit faster this time. We'll say that u is equal to half the speed of light, so c over 2. And again we can ask, well, if the man by the side of the road measures the speed of the light, how fast does he say it's travelling? If we were to go back to the equation we wrote down previously, v is equal to v prime plus u, our velocity addition formula, then we'd have c plus c over 2, so we'd have 3c over 2. This is a speed that's obviously greater than c, so it's faster than the speed of light. And you might very well know that's going to be a problem. We don't want things to travel faster than the speed of light. That's not what we observe in practice. So we might worry that maybe this equation isn't correct, or at least it's not correct for light. But if we didn't know that, we might very well just accept this result and say, well, yes, that's what we'd expect the man to see. What's the problem with that? To understand why this led to a problem, we need to look at what was happening at the end of the 19th century. So James Clerk Maxwell and others have done a great deal of work on understanding electric and magnetic fields. And in particular, Maxwell had written down what we now call Maxwell's 4 equations. These equations, if you manipulate them, allow you to predict the existence of a wave. And you can figure out the speed of that wave based on some other fundamental constants. And it turns out the speed of that wave is 3 times 10 to the 8 meters per second, which of course is exactly what we measure for the speed of light. So it's not a great leap then to think, well, perhaps light is a wave in electric and magnetic fields. And of course we now know that it is, and it's one form of electromagnetic radiation. What those equations don't tell you is what that speed is relative to. So we just saw in the previous example that it really mattered whether we measured the speed of the ball relative to the skateboarder or relative to the man standing by the side of the road, because we got a different number. So it wasn't really clear when we talk about light travelling at c, 3 times 10 to the 8 meters per second, what's that relative to? It also wasn't that clear what is light really a wave in, because we can send light through a vacuum, and it's kind of hard to imagine what a wave in a vacuum is. So one idea people came up with was something called the ether. So the idea is there's some kind of material that fills all of space. And it's this material that electromagnetic waves, such as light, are formed in. And again, this is obviously quite a strange material because we can't really seem to detect it. We don't feel it ourselves when we walk around. And yet somehow it supports this really, really high speed wave. One possible way to detect the ether is to move around relative to the ether and measure the speed of light. And if it was the case that the speed of light, c, is always measured relative to the ether, then when we move relative to the ether, we should, applying the velocity addition rule, measure a different speed for light. So this was an experiment that was first really conducted by Michelson and Morley. And the way they conducted the experiment was to make use of the Earth's motion around the Sun. So if we're on the Earth, we're travelling around the Sun at some very high speed. Now, if we're imagining the ether is filling all of space, then of course it's possible that at some point in our orbit we're at rest relative to the ether, and so we should measure, if we take some light and measure its speed, we should measure c, 3 times 10 to the 8 meters per second. But then at every other point in our orbit, we're going to be moving in a different direction. So it can't possibly be the case that we're always static relative to the ether. So if at various points on our orbit we measure the speed of light, say in this direction, and then the speed of light in this direction, we should expect those two numbers to differ at most places. So Michelson and Morley did this experiment using an interferometer, which we're not going to go into now. But the key result was that however they measured the speed of light, as in wherever they were on the orbit around the sun or in whatever direction they looked, they always got exactly the same value, 3 times 10 to the 8 meters per second. So what this tells us is there is something quite strange about light compared to the everyday objects that we normally have experience of. If you throw a ball and then I run around and I look at the ball, I'm going to measure something different for the speed of the ball depending on how fast I'm moving relative to you. But if you shine some light from a torch, then even though I was to run alongside that light at some speed very close to the speed of light, and I was to look at that light, I would still expect to see it shoot past me at c, 3 times 10 to the 8 meters per second. And it turns out that simply accepting this fact, along with some other basic ideas, is enough to develop the theory of special relativity. To get some insight into why all the weirdness of special relativity naturally follows from this insight that everyone measures light to travel at c, we're going to imagine a thought experiment, and it's a thought experiment called the light clock. So the idea is that we have two mirrors and we're going to bounce a pulse of light between those two mirrors. And we can imagine this as a clock because every time the pulse of light hits one of those two mirrors, this is a tick of our clock. And now we've put this clock on a spaceship and we've sent the spaceship out at some high speed. And now we're looking at it as though you were sitting on the spaceship, so you just see the pulse of light bouncing between the two mirrors. But now imagine you were standing on Earth and watching the spaceship go past. Rather than seeing the light move up and down, you would essentially see it following a zigzag type pattern. Because as well as the motion of the pulse of light from the spaceship's point of view, up and down in this diagram, we also have the motion of the spaceship going from left to right in this diagram. So let's draw out what we actually see here. So remember, we have one clock, but we're looking at it from two different points of view. From the point of view of the person on the spaceship, we simply have the two mirrors, and the pulse of light is moving from one mirror to the other mirror in one tick of the clock. For the person on Earth, because the spaceship and the clock on the spaceship is moving, they don't see quite the same thing. They see the pulse of light moving in this direction because the mirror has moved in the time it takes the pulse of light to get across there. For the person on the spaceship, let's say that the time they measure for the pulse of light to get from one mirror to another, they call tau, the Greek letter t. Now, everyday experience might tell us that a person on Earth will measure the same time interval, but let's pretend for a moment we don't know that, and let's say whatever they measure we're going to call t, a normal letter t. The person on the spaceship sees the pulse of light move a distance which we'll call d between the two plates. So we can draw the same distance in over here. But what you can see straight away is that the distance the pulse of light has to travel, as seen by the person on Earth, is not equal to d. That is one side of a triangle, but they see the pulse of light move along the hypotenuse of the triangle, which of course is larger than d. We can work out what d actually is. So if the pulse of light is moving at a speed c, the speed of light, and it takes a time tau to get between the two plates, then because we have distance equals speed times tau, we simply have d is equal to c times tau. This is exactly the same distance d from the Earth's point of view, so again that must be equal to c tau. So the question is then, this distance that the person on Earth sees the pulse of light travelling, let's call it h, what's that equal to? Well, again, they see the pulse of light travelling at the speed c. We've agreed that everyone must see light travelling at c. They say it takes a time t to get across there, so h must simply be equal to c times t. And now we're saying the distance h is larger than the distance d, i.e. the person on Earth sees the pulse of light travelling further than the person on the spaceship sees it. If both agree on c, they both agree the speed of light is 3 times 10 to the 8 meters per second, then that means that tau is not equal to t. Or in other words, the person on Earth says the pulse of light takes a different amount of time to get between the two mirrors compared to the person on the spaceship. Now, if this was a ball rather than a pulse of light, we'd have something a little bit different. Now, the two observers wouldn't agree on the speed of the ball, because the person on Earth would say, well, it's got the vertical component, the same as the person on the spaceship sees, but it's also got a horizontal component of speed. So the resultant speed along the hypotenuse will be greater. But because we're saying that everyone sees the speed of light to be c, now we're forcing tau to not be equal to t, i.e. the two observers aren't going to agree on how long it takes light to get from one mirror to another. And we can actually write down an equation that links tau and t. Over here we've already got two sides of a right-angled triangle. If we want to know what the third side is, we just need to know, well, how far has the mirror moved in the time t? Well, that's simply the speed of the spaceship u multiplied by t. Distance equals speed times time. So now we have that c squared t squared is equal to u squared t squared plus c squared tau squared. This is just Pythagoras' theorem. If we'd like to get this rearranged for t, well, we can write down that c squared minus u squared is t squared, so I've just taken the u squared across. So that's equal to c squared tau squared. And then I've got that t, that's equal to tau into the square root of c squared over c squared minus u squared. And we don't normally write it like that. We normally divide top and bottom of this fraction by c squared, which of course we're allowed to do. So that's then equal to tau into 1 over 1 minus u squared over c squared. So if I divide c squared by c squared, I get 1, and if I divide u squared by c squared, I get u squared over c squared. So now we see that t is not equal to tau. It's got this factor difference, which we call the Lorentz factor or the gamma factor. We usually give it the symbol gamma. It's telling us that two observers are not going to agree on time if they're moving relative to each other. So this is the beginnings of what we call time dilation. In the next video, we're going to start doing this a bit more rigorously. So we're going to start talking about frames of reference and how we make transformations between frames of reference. And we'll see that what we've shown here, using this, you might think perhaps contrived example of the light clock, is actually a general effect that's always going to occur whatever kind of clock we use, including our own body clocks. So please don't forget to subscribe, and I'll see you in the next video.